polarization process in the ferroelectricity, in the ferroelectric materials, it depends on the electrical field being applied. Okay. Once the electrical field applied, so you can reorientate the speed. Okay. And then once the electrical field released, so it still remains. Okay. We call it remnant polarization after electrical field is removed. Okay. So there's a electrical field. So typical in the ferroelectric materials you have. Okay. And piezoelectric materials also called ferroelectric materials. So now I want to introduce about some quantity. Okay. Usually there's some quantity. If you have you wanted to talk about the piezoelectric coefficient, so-called D. Okay. Okay. D is a piezoelectric coefficient, which is very famous to read in the paper. So usually there is two relative quantities, okay, such as the stress or force on the ceramic element in the prime. Okay, so for example, if you apply, you could have making the dimension change. Okay, making the dimension change. And this dimension change is also relative to the how strength be deformed. Okay, and this is the direction. Okay, if we wanted to talk about the piezoelectric coefficient, usually you have the three direction. Okay, one. Usually we have x, y, and z. And this y and z usually we quantitatively, okay, we call 1 for x, 2 for y, and 3 for z. Okay? Usually for if we want to number the x direction, y direction, z direction, we using the number. Okay? Using the number. And still, you could have some of the shear stress applied on the x direction, we call 4. Shear stress applied on y direction is 5. Shear stress applied on z direction is 6. Okay. So x, y is represented by subscribe 1, 2, 3 represented, and then shear stress. Okay. 4, 5, 6. 4, 5, 6. Apply x, y, and z. Six. Respectively. Okay, so 5, 4. Let's move 4, 5, and 6. Okay. Which means shear stress. So So why we wanted to talk about that? Because you could see there's a piezo charge constant, for example. Piezo charge constant usually using E to denote, right? For representing, okay? So there's a polarization generated per unit of the mechanical stress applied to piezoelectric materials. Let me just show you an example you could know about that. For example, you have D33, okay? D33. D33, that means for the direct piezoelectric coefficient. That means the induced polarization in direction of the 3. Okay? The first subscribe. Induced polarization. At the direction 3, okay, in direction 3. Per stress okay, per stress applied in direction 3. Okay? And then part the upper, this is direct piezoelectric effect. Second, alternatively, if there is a converse, piezoelectric effect, it will be, say, induced stress. Induced strength in direction 3. Per unit electrical field. Apply in direction 3. Okay? This is all the same direction, direct and converse. Okay? And now, if we have D33, 31, okay? D31 for direct, effect, D31, it represents induced polarization in direction. Direction 1. Direction 3. Okay, per stress applied in direction 1, right? So this is the polarization. That means induced polarization, right? Induced polarization is because of the stress applied. In direction 1. This is also x direction, right? Also x direction. So the first subscript is the induced polarization in x, in not x. This is which direction? X, Y, D. Z, right? Z direction. Right? Okay, Z direction. Okay, for the converse, piezoelectrical effect. If today I ask you what is the D33 converse, D31, okay? For the converse piezoelectrical effect, what is the definition for the D31? Converse electrical field, that means converse piezoelectrical effect, that means we have to apply electrical field, right? Apply electrical field and create what? Create the strength change, right? Right here. Induce the strength in induced strength. In direction. Which direction? Direction 1. Per electrical field, right? In direction 3. So which means here is applied electrical field. And this is the induced strength in direction 1. This direction is the x direction, right? Right? Apply electrical field, induce strength in direction 1. Because opposite, right? That's opposite. Is that okay? So you can also utilize, for example, take one example D. I should not remove. But it's okay. For example, direction 1, 5. Right? 1, 5. Let's use this example. 1, 5. What is the 1, 5? 1, 5. The first is induced polarization, right? Induced polarization. Induced polarization. This will be changed to 1, right? And per stress applied to which direction? phi direction, that means
Y.
y, yeah. Remember about this phi is the shear strength, right? Shear strength. Okay? And then converse 1 phi. Induce the strength in the one direction, right? 1 phi. Induce the shear strength. Shear strength, right? This will be shear strength in one direction, which is x, right? The first subscribe, right? And then the second subscribe is the electrical field applied, right? Oh, sorry, in two directions. This will be induce shear strength in two directions. Yeah, shear strength in two directions. Why? Because it's here, right? Okay. Induce shear strength in y direction. Shear. Direction, right? In direction 2, right? And then per electrical field applied in one direction, right? Per electrical field applied in one direction, right? One direction. Electric field applied in one direction, right? Induce shear strength, right? In the y direction. Because phi is the y direction, right? If here I change it to 6, that means induce the shear strength in z direction, right? Is that okay? Okay, so, and so on, okay, and so on. So you have many, you can take example for D2, 3, right? 2, 3. D2, 3 doesn't mean D2, 3 doesn't mean here. Induce polarization in the y direction, right? D2, 3 in y direction. Per electrical field applied, this is electrical field. This is polarization, right? Right? This is polarization. This is for the red. Right? And then converse. If converse D2, 3, you have applied electrical field. The applied electrical field is external. And 3 is a shear strength. Sorry, it's not shear strength. It's this will be strength because I'm the z direction, right? On the z direction. Is that okay? Let me write it. D2, 3, the red. D2, 3. Okay, you can take this as an example, okay? D2, 3, that means the first subscribe is polarization, right? Induced polarization by electrical field. And this electrical field is from the three direction, right? Three direction, that means Z direction. So this is induced polarization. Induced P. And then
the slide says that there should be stress applied in direction 3.
yeah, stress. Yeah. Stress. Sorry, stress. Stress. Direction 3. So this is Z direction, right? Yeah. Okay, and converse. Converse what? The first subscribe. Huh? Apply electrical field. Yeah. Electrical field in Y direction, right? Right. We also call 2 per what? Induced stress. Yeah. In Z direction, right? In Y direction. Sorry, Z. Right? Is that okay? This is if you know about one example, you can change everything. Okay? And we call this is a piezoelectric charge. Okay? Piezoelectric charge constant. There's many constant. Okay, many piezoelectric coefficients. Okay, so all of them are using the same nation. Okay, the same nation to represent about piezoelectric constant. So-called usually like a zinc oxide. Okay, why we wanted to talk about that? Like a zinc oxide crystal, because the polarization is aligned Z axis. Okay, so we have to apply force on the Z axis, right? So therefore, usually if we have, for example, AFM tips force on this direction, it could generate the electricity. We can measure the electricity output. So therefore, we have a D33 constant. Okay, we get a D33, which means apply a stress right on Z direction and get the output of electrical field. Okay, all the electricity also on Z direction. Okay, and there's no constant because for the zinc oxide it only has a polarization on Z axis. There's no polarization on X axis. So-called D31 is almost 0. I would say almost 0. So the constant will be 0. Okay, constant will be 0. So as you can see, if you read some paper for the zinc oxide, you could see only D33. Okay, that means apply the stress on Z direction, get output of the piezoelectricity on Z axis. Okay, and then converse is just explanation is opposite. Yeah, apply electrical field and get the dimension change. Okay, the same direction. Okay, so that's why we need to use this nation for represent everything constant. So you have the array. Okay, array. Okay, for example, D11, D12, D13, D14, depends on what materials, okay, what symmetry material we have. You have this piezoelectric constant. And some of the material, for example, zinc oxide, this will be 0, 0, 0, and only D33, for example, D33 has a value, okay, has a value. Okay, so we can use this for calculation output, okay, piezoelectric output. Okay. So this is one example that you can take as a reference. Okay. Okay. Just imply to you, this will be shown in the final exam. Okay. This will be shown in the final exam. So we will take a practice. Okay. Piezoelectric nano generator, we call it PNG. Okay, PNG. Tin oxide, tin dioxide. Okay, this is just as I mentioned last week. Do you remember? I make a device, right? Many device, and then because of the temperature difference in the oven, so therefore my device is destroyed, right? So I'm using these materials. Okay, I'm using a zinc tin oxide materials. This zinc tin oxide can be grown by CVD process. And then by CVD process, I can grow the tin oxide, liquid tin oxide. This is also ferroelectrical materials because it is a perovskite. Because this is a perovskite, so I can grow these materials on the substrate, right? On the substrate. And then I pick up single nail build because it is the micro build, micro wire. It is large. So I can use some of the tissue and then to pick up single micro wire and then embedding on the plastic substrate, okay, plastic substrate, and then bending, okay, bending to measure the output electricity, okay. So this is the unit cell, okay. Okay, take this unit cell to see, okay, you have two clusters. One is ZNO6, another one is SNO6, okay. So they pack together. You can see, the unit cell you can see right here. You have SNO6 and DNO6. The bottom side, okay, is DNO6. The upper side is SNO6. So remind you well to here. Bottom side, this is the zinc atom in the center. So have you seen that this is the lower deviation, right? If you look about the top side, another artificial cell has SNO6. Here is a tin ion. Tin ion has an upper deviation, right? So they align together. Here is a tin. Here is a zinc. Okay? Both they align Z direction. So they have the net polarization. Is that okay? Because this distance and this distance is difference. So they have the net polarization align this direction. But if we look at about the x direction, there's a symmetry. So there is a non-net polarization on the x direction. So which is simple. You just need to monitor what polarization of the materials has, in which direction, right? In this direction is similar to zinc oxide. So they have the net polarization on the z-axis. So you just only need to apply a stress on the z direction, and they can produce the electricity. If you apply the x direction, y direction, there's no output because the D in the x and y direction and y direction is a 0. Okay, is a 0. So this is what I show you. Okay, I pick up one single microwire, this is needle-like, and then embed it on the plastic substrate, okay, on the plastic substrate. So this is the PS substrate. This is the PS substrate. So, and then we mounting the silver on both sides, right? So this is a console simulation, okay, console simulation. If I apply the stress, okay, I apply the stress on it, so which can generate the output voltage about plus minus 86. And then this is the tensile strength. If I apply the compressive strength, it generates positive 86. So you may curiously ask me, Professor, what you define the positive? What you define negative? Right? It depends on you. It depends on you. It depends on, because the tensile strength can be output plus, but compressive strength output will be minus. So it doesn't matter. It's okay. But if I apply tensile strength, generate the negative charge, and then compressive strength, it will be opposite. The sign will be opposite. Is that okay? Okay? Because the tensile strength has an output value, right? For example, positive 10. And compressed will become negative 10. This is the definition. Yeah. It doesn't matter, okay? And then now there's also size. Okay, size different. Bigger size, large size has a large output value. So now I would this value, can I have some benchmark? This material is the ferroelectric materials, which is much higher than, I would say maybe 5 or 10 times higher than. It depends on the material's property. The piezoelectric coefficiency will be much higher than tin oxide. Okay, so that's why I use these materials. Okay, to grow on the substrate. Okay, and then now I explain about this electricity. Okay, electricity. This is the output, right? The output sample you can see, because both sides silver is electron. Okay, is an electron. So as you can see, here is an IV curve. Okay, here is the IV curve. Here is a zero, almost a zero, right here. And this is SMG1 is one generator. SMG2 is another generator. So can you tell me about the IV curve? This is the Schottky behavior or the ohmic behavior? Ohmic contact. This is Schottky or ohmic. This is the Schottky behavior on the single side. Right? Because we have discussed about the metal and semiconductor, right? Metal and semiconductor IV curve. If this is I, this is V, right? This is ohmic. Ohmic contact looks like that. Schottky contact will looks like that, right? Okay? Schottky contact. Some of the device exhibit only single side Schottky contact. This device exhibits something like that, single side. I mean, single side. That means another side is not Schottky. For example, looks like that. Or another side will be ohmic. Is also possible. Okay, this is only one side is Schottky behavior for SMG2. SMG2 the same inhibit single side Schottky contact. A single side Schottky contact, I can use this, right? This is like a dial, right? Already I showed you in the chapter 3, right? This is looks like a dial, chapter 4, okay? The symbol is the dial, right? And then this is a dial, okay? This is a dial, this is another dial, right? Another dial. Okay, so now, this is SMG1. Get the output. This looks like the AC signal. This is the output value voltage. This is a function of the time. So you can see there's a peak up and down, up and down, up and down. This is SMG2 output. It's a green color. Okay? You have the output up and down, up and down. Okay. And then now I package it in series packaging. You get the output almost the same, but sometimes slightly higher, but almost the same. This is justify that both nano generator can be superposition. You know, superposition doesn't mean plus one, SMG1 plus SMG2, superposition, 叠加, okay, superposition. And this is the in parallel, right? In parallel output, you could see this is a SM current output, right? If you have one device, SMG1 is output current looks like that. SMG2 output current looks like that. And then you superposition 1 plus 2, you get 1 plus 2, right? So now, as I wanted to introduce, how come the nano generator looks like an AC signal? Okay, AC signal. So this curve that we prove, this is like a battery. Do you understand? This is like a battery because two batteries in series packed together, and then their output is slightly higher. But of course, they still have some resistance. It cannot 1 plus 1 larger than 2. You still need to consider about the resistance between the device. So therefore, this value is not always, you know, is not over than 100. But for the current, you could see almost it's reach to hundreds. Okay, reach to hundreds. Okay, now I wanted to introduce about this is almost a 0.1 voltage and 50 nanoamp. Okay, let's look about how this mechanism will look like. Current is generated. Okay, the current is generated to the AC signal. Okay, to AC signal. So if we look about this diagram, okay, this diagram, we remember about this. Okay, this is the Schottky contact, one side, right? Because I only measure, I get this is 0 is right here, right? 0 is right here. So you can see this curve, 0 is right here. So almost on the 0, and here is almost the only contact. So only one side Schottky contact. Is that okay? 可以吗? It's only one side. Looks like that, right? This curve looks like that, right? This is 0, and here is 0, right? So this side, right hand side, from the 0 to right hand side, almost only contact. So we don't need to consider about the only contact. I just consider about one side Schottky behavior, right? So this is a representative band structure. Okay. Externally, this is the nano wire, right? So I represent, right? There's a one side Schottky behavior. So this is a one side as a die. Is that okay? If you have both sides like that, right? And then you have to use this. You have to use this. If you have both sides, for example, right? It will look like that. But because only one side, right? The device will look like that. Okay? And this is the device SMG1. Okay? So for the Venn diagram, because one side has a Schottky contact. So Schottky behavior, that means you have the Schottky very high, being established as single site, right? You have the Schottky behavior, right? If you only contact, you don't have the Schottky very high. Is that okay? Oh. So therefore, one side Schottky barrier on the one side. Maybe you will ask me, how you don't want to put on the left-hand side? Yeah, of course you can put on the left-hand side. Same result. Now I take an example. One side Schottky behavior, so one side there's a Schottky very high being established. This is at the original state. Original state, that means you don't need, there's without strength, right? Without strength. So there's a Fermi level is right here. This is the conduction band. This is the valence band. Okay? Now, as I apply the stress, right, on the z direction, because this I embedded the nanowire on the z direction, right? So therefore I apply the stress compressive. Okay? So what happened? You can look about that. Because one side Schottky behavior being established. So I'm assuming that once you apply a stress, okay, they create an electrical field, okay? Suddenly, piezo potential, this we call the piezo potential being created, okay? Being created. So this piezo potential being created, which means this conduction band will rise, okay? Will rise. So as the conduction band will rise, okay? And then this will be here because there's a carrier, okay? Carrier will flow from the left-hand side to the external load to the right-hand side, okay? So at this moment, you could see it generate the electricity, okay? Generate electricity. And then this electron will flow to here. And then just accumulate on the Schottky behavior side and never float because this electricity resistance is quite high, right? So there's a Schottky very high, so just block the electron to the one side. Because the Schottky very high, just like now the door is being closed, so the carrier only accumulate on one side. Okay, only accumulate on one side. So therefore, if here I have an electrical measurement, I will measure there's a current flow to this way because electron flow to this way, current will flow to another way. So that means that external load will measure the output electricity. Okay, output electricity. So you could get A from A to B. You could get, oh, there's a highest. And then next is once I release, okay, it will become C to D. Okay. Once I release, that means because all the electrons being accumulated here, right? Being accumulated here, and then finally it will become neutral. Okay, it will become the neutral. So all the electrons flow to here. You will get the highest. Once the piezo potential, once you release, the piezo potential will be dropped because no piezo potential, right? Piezo potential. Piezo potential is based on the materials because as I simulate, there's a piezo potential being established, right? Based on the simulation, there's an output, right? There's an output. So therefore, if you think about that, because all the electrons being accumulated on the right-hand side, once the piezo potential release, because they release, right? So no piezo potential. So this will be dropped, right? Once it drops, because this side will lower than this side, so electron will flow back, right? Flow back to the left-hand side. And then progressively they will increase. And both sides neutral. So you will become C to D. Is that okay? Because this electron flow back. Okay? And then now you could have two questions. Another question is that, Professor, why you assuming the piezo potential is on the left hand side, right? Why you don't want to assume it on the right hand side? You also can assuming the piezo potential can establish on the right hand side, which will be the same because this piezo potential being established in the right hand side, which will be the highest, right? Will increase the highest as well, right? So you could get the electron will flow back, right? Because this Fermi level is high, right? So the carrier on the highest will flow to the left hand side. So you also will get the output current is negative. Once the piezo potential release, this will be dropped, right? And then dropped, all the electrons accumulated on the left hand side will flow back, right? So the signal will opposite. Do you understand? So the piezo potential on the left hand side is right hand side. It doesn't matter. Okay? It doesn't matter. It is the signal's difference. Is that okay? I explain again. So piezo potential is just definition assuming by yourself. You can assume it on the left hand side or assume it on the right hand side. Okay? But how there is a piezo potential? Because we have calculated there's a piezo potential. Okay? Simulation tells us. And also piezoelectric constant tells us there has a piezo potential. So they must have the piezo potential be created once you apply the stress on the z direction. That we already mentioned, right? We already mentioned in the previous slide. If I apply the stress on the z direction, of course, create electricity, right? So this electricity is the piezo potential. Okay? Okay? So I explain again, okay? I explain again. No more battery. Okay. Maybe I have to quickly. Almost 20. Okay, almost 20. Okay, I quickly explain again. Okay. Because there is a one-side Schottky barrier, okay, one-side Schottky barrier. So you can plot the band structure looks like that. So one side Schottky behavior, so you have the Schottky barrier height established on the one side, okay? And then once I apply a compressive, so create the piezo potential on the single side. So this piezo potential create on the left-hand side, so you will left the conduction band, right? And then because on the conduction band has some carrier, so therefore the electron will flow from the left-hand side and then accumulate on the right-hand side. And because right here there's a Schottky barrier height, so therefore the electron only just accumulate here, being blocked. Okay, so you could see because here if you have the electrical measurement, you could get there's a current being generated, right? So you could see A to B because the electron flow here to here, and then this will be progressively drop, right? And then finally cancel. Finally neutral. So therefore you get a higher current and then finally reach to the balance. Okay, balance. And once release, okay, piezo potential disappear, drop to the just drop, okay? And then this electron, because the original being accumulated on this side, right hand side, will flow back. So at this moment the electricity you will get the difference opposite electricity. So you will get the current is opposite. Okay, and then because once the electron flow to here, you will progressively increase the Fermi level, right? Fermi level. So finally reach neutral. Okay, so we will reach to the neutral state. Okay, so A and B, C and D. Okay, that's the mechanism. Okay, tell that wow, there has an AC signal being generated. And how it becomes the DC, we already mentioned. If you have a diode, you can use the DC to switch. Okay, switch to from AC switch to DC. Okay， 你可以用整流器，整流器就可以整流成 DC. You can use the rectifier circuit to convert from AC to DC. Okay. Okay, let's finish today.
ठीक है उसमें क्या हुआ एकदम क्या हुआ एकदम हाँ उसको ठीक देख लिया हाँ जैसे ही है ले नीचे सीट को तो नीचे बैठ